So let's take a look at how we can use the second fundamental theorem of calculus for word problems. So according to this, g of x is equal to the integral 1 of x f of t dt, and this graph is the graph of f. Okay. So key thing is we gotta take note of what this actual graph is, and just as a reminder, this is a graph of f. Okay. Anytime you see one of these graphs, what do you usually end up doing? Yeah, we have to take the areas. So if I color these in, let's use the highlighter since it's easier. Here is a triangle, right? I have another triangle right here. I have another a rectangle right here. Triangle, triangle, oops, sorry, one of those rectangles where I have to subtract the semicircle, and then another triangle right here. So if we do these quickly, 1/2 my base is 1 times my height is 2, which gives me an area of 1. Over here I have 1/2 my base is 3, my height is -2, which gives me a -3. Right here, I have a rectangle, so the length is 4 and the height is 2, which gives me a -8. Sorry, -2, which gives me a -8. Here, 1/2 my base is 1 times my -2 gives me -1. And then here I have 1/2 my base is 2 times 4 gives me 4. Let's save this for last because they're always fun. Now 1/2 my base over here is 1 times 4 gives me an area of 2. Now finally, let's do this. My rectangle is 1, 2, 3, 4 across, 4 tall, which means it's 16. Then I subtract my semicircle. Radius here is from here to here, which is 2. So 2 squared is 4. 4 pi divided by 2 is equal to 2 pi. So let's keep this in mind as we do the following problems. So I believe you guys have these. Let me make sure I get us in the right range. Alright. So you have this picture with you. So you have a bigger version. And we're going to write these out right here. So the first one says g of -4. According to this problem, g of x is equal to the integral from 1 to x f of t dt. So, if I have g of -4, doesn't that mean I can redo this whole thing right here? Oops, sorry. And everywhere I have an x, I'm going to plug in a 4 instead. So, I'm going to erase this x right here, this x right here, and then we are going to plug in our -4. So here's -4 in here, and I get -4 in here. So what I end up doing is I go from +1 all the way to -4, which is here. Since I'm changing my direction, I end up getting negative the sum of that area. So if I add from 1 to -4, get -1 minus 8. And don't forget, I had to stick that negative sign because I was going from right to left instead, which then gives me a -9 inside times that negative gives us a +9. So up here I would put in a positive 9, right? So I'm going to do this again, but this time, oops, sorry, wrong one. Oops. The next problem, sorry, again. Ooh, let's move this. Come on, come on. There it is. The next one says g of 1. So let's erase our x's and plug in a 1. And this should be good. So if I plug in a 1 here and I plug in a 1 here, we know that there is a property when I go from a lower limit and an upper limit that is the same. And that is that my answer has to be 0. Good. Once again, I'm going to do this again. Come on. Oh yeah, there it is. Okay. Now it says to plug in a 3. So I'm going to erase my x's right here. I'm going to plug in a 3, which means I need to go from 1 to 3. And if I take a look at 1 to 3, here's where 1 is, and here's where 3 is. So that means my answer here has to be 4, right? Don't even have to do any calculations there. Finally, I do the same thing. Oops, not that one. Do the same thing, but I need to plug in 8. So once again, I erase my x's right here. I plug in my 8, which means I have to take the area from 1 to 8. And if I take a look at that, it's everything in this triangle, this rectangle that cuts out the semicircle, and this triangle right here. So I get 4 plus 16 minus 2 pi plus 2. So if I add all my whole numbers, that gives me 20 plus 2 gives us 22 minus 2 pi. Good. So this isn't necessarily anything new. All we're really doing is, sorry, that's a pi right there. Ugh, that's not good. Let me undo that. Let's delete this entire section. And if I rewrite this, we get 22 minus 2 pi. Okay, yeah, that's a pi right there. Okay, so none of that has really been anything new. All it is we are given the formula in a different way and we have to plug in. So let's go ahead and take a look at the second half of these problems where it changes just a little bit. So what we see is this first one says I need g prime of 0. So let's go ahead and take this equation we have. If I want g prime of x, I need to take the derivative dx integral from 1 to x f of t dt. So if we take a look at the fundamental theorem of calculus, the second fundamental theorem, I have a derivative, I have a constant in the bottom, an x on the top, and an f of t dt. So doesn't that mean that g prime of x is actually equal to f of x? Right? So what I end up doing is I notice this graph is actually the graph of the derivative. So g prime of x is actually the same as f of x. So what I end up doing is I go to 0 and I see that f of x, which is g of x, is actually at this point 0, comma, negative 2. So in this case, the derivative's value is negative 2. Also, if I look at g prime of 5, that means I need g prime. So let's see, if I wrote this, let's do the first one. G prime of 0 is equal to f of x, or sorry, f of 0. Let me do this, let me type this out because computer's not liking me right now. So I could say g prime of 0 is equal to f of 0, f of 0, which according to the graph, because this graph is f as it says, at 0, my value was negative 2. So this gives me a negative 2. And that's where I get that negative 2 up here. If I do this again, I see g prime of 5 is equal to f of 5, which means I go to my graph, and if I look at the number 5, 1, 2, 3, 4, 5, my value is at a positive 2. So I see the derivative has a value of positive 2. And that's what we get over here. Good. And so now we want to take a look at g double prime. Well, if this is the graph of the derivative, isn't g double prime the slope of the derivative? So according to this, g double prime of x is equal to the slope of the derivative, which means I need to find the slope at these points. So if I take a look at g double prime of 5, 1, 2, 3, 4, 5, my point is right here. So let's use a highlighter to mark it. Isn't that point right here? Let's actually use a different highlighter. That point is right here. If I take a look at the slope of the line over there, let's use this mini pen. Isn't my slope a horizontal line? And we know that all horizontal lines have a slope of 0. So our slope at g double prime of 5 is 0. The next one looks for the slope at g double prime of 1. So here's 1. And if I look at 1, don't I have a straight line? Please pretend that's straight. Actually, let me use a straight line. Don't I have a... Well, yeah, that's as close as I can get. So, don't I have a straight line right there? Well, we know that the slope of a straight line is the rise over the run. And if I take a look at this, I rose 2... Let me use a better marker. I rose 2, and I ran 1. So 2 over 1 is equal to 2. So what we end up seeing is g prime of x are the y values. And we see the g double primes are the slopes. So it's just like reading our old graphs before, except we're taking it one step further. Alright, so we can actually answer a couple more questions with this. And so what we're going to do is we're actually going to review when we're taking a look at a little bit of curve sketching and interpreting graphs of derivatives. So what we notice is we can actually still figure out what's happening to this graph, right? So just for the sake of making things easier, I'm going to use a plus sign, right? So here's my plus sign, here's my minus sign. And what I want to do is I would like us to label these pieces like we used to, where we said we were increasing or decreasing. So let's use let's use this color. It's a little nicer. So what we notice is, oops, let's clone this. Infinite cloner. So what we end up seeing is on this side of the graph, everything is positive, right? And then what I also see is everything here is negative, and below, the values are below the x-axis. So actually I see that this right here, let's group this, gives it easier for us. This entire section, isn't it negative? I also see that everything on this side is positive. So let's go ahead and drag in my positives, and I'm going to clone them. Remember when we did this a couple units ago? So let's go ahead and interpret what this means. Oops. Group, copy, oop, wrong one. Ah, sorry. I'm gonna copy this, and then we see copy, copy, copy. Everything up here is positive, right? Do you remember what this meant? Don't the positives mean I'm increasing? Right, so this right here means I'm increasing. Here, this entire section right here means I'm increasing. And then didn't this entire section here mean I'm decreasing? Decreasing. So this to here is decreasing. So just as a reminder, if I go increase, decrease, sorry, that's a bad sketch. If I go increase, let's use the actual line. Increase, decrease, and then increase. Can't I label certain parts of this graph? Right. Also, what do I know about these slopes? Well, let's go ahead and change these colors, because we know that we can use these to actually label our slopes, which then become, let's use, I don't know, this is a pretty good color. Let's say we use these. Couldn't we label our slopes? And our slopes tell us about concavity. So we notice right here, and just because it's easier, I clone this. Weren't all my negative slopes right here? Anything going downwards, tell me I'm concave up or concave down. So I'm going to continue drawing these. Negative, negative, negative. I'm going to spread these out all the way to here. Aren't I negative? I'm also negative, and let's just copy these right here. I'm also negative over here. So once again, let's copy these. Negative over here. Negative over here. Negative over here. We already said our slope was 0 over here. We're also negative on this side. Right? Didn't we used to label these that way? I'm just going to continue labeling these as negatives. Well, couldn't I then label, let's do this right here. Let's go ahead and clone these ones. Couldn't I label all of these as positive because they're increasing, the slopes are positive. And so if I continue, right, plus, I also have pluses over here, so forth. So we're going to continue labeling our graph because we can actually interpret these things. What's the slope right over here? Good, I hope you said 0. So the slope there is 0. I'm just going to drag this over here so it helps us remember. And I'll color code it as well so that we know why it's there. So let's go ahead and answer some of the following questions. It says, state any local minimums of G. Well, according to my interpretation, I went increase, decrease, increase. So according to this, I should have shifted these over, sorry. My negative stopped here. My positive was here. So where do I hit my negative value? Good. So I'm going to type this in and hopefully I can squeeze it. So at x is equal to 1, comma, since g of 1 is equal to 0, right? And g changes from negative to positive, we have a minimum at 1, comma, 0. And if I make this smaller, fit perfectly right here. Sorry, I can't get this to be bigger. But at x is equal to 1, since g of 1 is equal to 0, and g changes from negative to positive, we have a minimum at 1, comma, 0. And we get the value 0 from our previous problem. When we found g of 1, we found the answer was 0. The next question says, what is the maximum value of g on the interval negative 8 to 8? At what x value does this occur? So if I look at my graph, I do note that this is a closed interval, so I have to check the endpoints. So there are two places I can have a maximum. The first place is over here, where I go from increase to decrease. The second place is over here because it's an endpoint. So I see that this happens at g of 7, or sorry, negative 7. I also see that this happens at g of 8. G of, oops, g of, let me use a pen. I see that this also happens at g of 8. No wonder it looked like that. Well, we actually have the answer for g of 8. The answer for g of 8 from our previous problem was 22 minus 2 pi. We gotta find the answer for g of negative 7, which means I go from the integral of 1 to negative 7 of this function. Right, so I'm gonna say f of t dt. And so what we see is I have to first of all, oh sorry, there's a dt. I first of all, d parentheses dt. First of all, I have to switch these answers, so, change my sign to to negative. I have to change my sign to negative because my integrals are incorrect, not incorrect, but they're flipped. So I have negative parentheses, and I go from negative 7 all the way to positive 1, which gives me negative 3 minus 8 minus 1, gives me negative 12. And so we see that the g of negative 7 has to equal positive 12. Well, so I take a look, who's a bigger value, 12 or 22 minus 2 pi? If we approximate and we know pi is 3.14, 3.14 times 2 is approximately 6. 22 minus 6 is approximately, what is that? About 16. So which one is the bigger value, g of negative 7 or g of 8? Good. Your answer should be g of 8, since g of 8, since it equals 22 minus 2. I'm going to write the word pi because it's easier for me. So we know this is where our maximum is. Last part says state the coordinates of any points of inflection. We know that we have a point of inflection when I go from concave up to concave down. So if I take a look, I have negatives, then I hit 0, and remember I'm looking at my purple plus signs. Then I have positives, and then I see them switch. I have a positive to negative right here, and that happens when x is equal to 3. Then I see I go from negative to positive right here, which is when x is equal to 5. And then once again, I go from positive to negative, which happens at, what is that, x is equal to 7. Yeah. X is equal to 7. And because it just says state the coordinates, so I have the x values, I gotta find the y values, so I plug all of these in. If I find g of 3, we actually found that answer earlier. We found g of 3 to equal 4, so that point is equal to 3 comma 4. If I find g of 5, we did not find that one earlier, so g of 5 is from 1 to 5, and I see that's this triangle right here, that's a positive 4, and 5 is half of this, which gives us 4 plus 16 over 2 is 8, plus 2 pi over 2 is pi, and I'm going to write pi again, and it was a minus pi. So if I simplify that, I get 12 minus pi, which gives us a point of 5 comma 12 minus pi. And finally, g of 7. And we haven't found g of 7, but 7 is from 1 all the way to 7, which then shows us we have 4 plus 16 minus 2 pi, which is equal to 20 minus 2 pi, which gives us the point at 7 comma 20 minus 2 pi. So we're combining all of our second fundamental theorem with our previous curve sketching information from the past. So that's a good review for AP type problems. That was a long video, but good luck.